Let's start now the lecture. So I've seen in the previous class that we have the conditional branch instructions. So these are the conditional branch instructions that we have seen. So I've seen that these instructions are short jump instruction. What does it mean, short jump instruction, Shabab? Shabab, can you hear me?
Yes.
Yes. What does it mean, short jump?
Like BN 0 and BN not branch if 0, branch if not 0. I think like it's maybe 7 bits.
Okay, so these instructions BC, BNC, BZ, BNZ, so they are 2 bytes instructions. So if you open the data sheet, so here you have the list of conditional branch instruction, for example, BC, BN, BNC, etc. So we have 2 bytes. Okay, let's use the highlighter. So for example, BNC, you can see that we have this instruction takes 2 bytes. 1 byte, the first one is called the opcode. Okay, so the first part here is the opcode. So this part, which is 1011 11100011. So this is the opcode. So here we have 8 bits to write the address. So with 8 bits, we can write addresses from 00 till 255. So we have a range of 256. So what does this mean? This means that if you have any program, so this is the DRA, for example. So we have the opcode, and then we have, this is the DRA, which is unconditional branch instruction. So same thing, we have the opcode, and then we have here 11 bits to write the address. For BC, BNC, for the conditional branch instructions, we have just 2 bytes to write the address. Okay, so for BNZ, so we as a user, for example, here we have to use BNZ followed by the label again. Now we have this instruction. The program counter is a register that is pointing to the next instruction. That means the program counter is here. Now from here, where is the label again? Again is here. So from the program counter, we have to make -1, -2, -3. So the code or the binary code of BNZ again will be E1 FD. E1 is the opcode. So this E1 is the opcode, operation code, and FD is the relative address. So FD, so if the last bit is 1, that means you have negative number, so you have to take the 2's complement to find its positive value. Okay, so FD means -3. So here our label is at the line -3. So here we can write 3. Then we have to make the 1's complement. Then we have to add 1. So this is the value of -3, which is the 2's complement of 3, which is FD. Here you have 13, and here we have 15, so which is FD. So that's why here the relative address here is FD. So this is a backward jump or forward jump, Shabab?
Backward.
This is backward jump. So we are repeating the execution of these instructions. Okay. We have seen also an example of forward jump. Here we have BNC and 1. So this is the line that we are executing. The program counter is pointing to this line. And here from this line, we have to go to the label L1. We have to make just 1 line. So the opcode will be the opcode of BNCN1 will be E3. E3 is the opcode, so you can find this opcode directly from the datasheet. So I have BNC. This is BNC, so the opcode will be 11110011. So here we have the E, and here we have the 3. So we have E3 followed by n bit to write the relative address. Okay, so that's why here we have E3 and or E301. Is there any question about this, Shabab? No questions? So here we are branching with condition to the label N1. So here, what is the absolute address or the target address of N1? So the absolute address, we have seen that the absolute address is nothing but the relative address times 2 plus the program counter. So in our case, the relative address is 01. So I have 01 times 2 plus, so we are executing this line. The program counter is pointing to this line, so the address here is 8. So we have 1 times 2 plus 8. So it is 10, which is 0x08. So you can see that the label N1 is at the address 0x08. Same thing with the backward jump. So here, let's calculate the absolute address of the label. So here we have BNZ again. So the target address will be at again. So this is again. So the absolute address should be, I have to activate the pen again. So the absolute address is here, which is the address 6. How to find this address? So same thing, the target address or the absolute address is the relative address times 2 plus the program counter. What is the relative address in this example? So program counter is here. We have to make -1, -2, -3. So the relative address is -3 times 2 plus, what is the value of the program counter? So we are executing this line. The program counter is pointing here. What is the address of this line? Yalla Shabab, we have seen this in the previous class. What is the address?
Yes, 9.
What is the address of this line? 9 is the number
C.
of line. So 1, 2, 3, 4, 5. So what is the address? C.
0C.
So the address is 0C. So plus 0x0C, which is 12 in decimal. So we have -3 times 2, which is -6, -6 plus C in hexadecimal. So the result will be 6. So 12 minus 6 will be 6. So that's why here you can find the target address here at the address 6. So this is true for all the conditional instructions. They have the same type, so they have the same number of bits reserved for the address. If we turn back to the data sheet, you can see that all the conditional branch instructions, they have the opcode on 8-bit, and then they have 8-bit for the address. So why we are using relative address? Because to write the target address, we need 21 bits. If you want to write the address, the whole address, we need 21 bits. But here we don't have 21 bits. We have only 8 bits. That's why we have to use relative address. And for this relative address, we have to divide it into backward and forward. So we can have -128 address above or plus 127 address after. Any question about this, Shabab? So here, from BNZ again, we can here make backward jump of -128 line, or So starting from the PC command, okay? Or we can have up to plus 127 line, okay? Now let's go now to the conditional, to the unconditional branch instructions. So what are the unconditional branch instructions, Shabab, that we have seen? We have Goto and BRA. Very good. So these are the unconditional branch instructions. Now, what is the difference between Goto and BRA? So for the job, they are doing the same job exactly. But if you go to the data sheet, what is the difference from the data sheet? This is Goto. Let's open the my writer. So this is Goto, and this is BRA. So what is the difference between them? For the BRA, how many bytes do we have to write the address to write BRA?
Have 4 bytes.
For the
No,
BRA,
2 bytes.
we have 2 bytes. We have 8-bit and then 8-bit. We have 16-bit. Whereas for the Goto, how many bytes do we have?
4.
4 bytes. So for the Goto, we have 1 byte, 2, 3, and 4. So this is the difference. This is the only difference. Now, with the Goto, how many bits do we have to write the address? With Goto, how many bits? How many K do we have?
We have 20.
20K.
12.
Very good.
Yeah, 20.
Whereas for the BRA, how many bits do we have to write the address?
11.
We have 11 bits. Okay, let's start with the BRA. So for the BRA, we have 11 bits to write the address. And then with 11 bits, and we can have a range of 2 kilo. Okay, so we have to divide this range into backward jump and forward jump. So starting from the PC, we can have up to minus 124 instructions or plus 1023 instructions. So this is the range of n. And how to represent negative number? By using its choose complement. Now, since we cannot go anywhere, so same thing, we have relative address. So we can have minus 1024 starting from the PC. And the PC means the address that is just after the address that the instruction that we are executing. So it is a relative address. So here for n also have to write relative address. Same thing, but instead of writing the address by using 8-bit for the conditional branch instruction, we have to do it by using 11 bits. Now let's see the Goto. So for the Goto, how many bits do we have? We have from K0 till K19. So we have 20 bits to write the address. Now, can we go anywhere by using 8 bits? By using 20 bit, Shabab, sorry, by using 20 bit, can we go anywhere? So to go anywhere, how many bit do we need?
21.
21, but here we have only 20 bit. Can we go anywhere by using just 20 bits? Okay, let's return back to the previous program. So what are the addresses here? So the first address is 0. The next address is 2, 4, 6, 8, A, C. What can you say about these addresses? So all the addresses, they are even or odd?
Even.
Even. And since you have even address, what is the first bit of any even number? Let's write the address 4. So we have 1, 2, 4, 8. So to write 4, we have 0, 1, 0, 0. Let's write, for example, 8. So we have 1, 0, 0, 0. Let's write A. So A is 10, which is 8 plus 2. So you can see that all the addresses, they are even, so that the first bit is always 0. Why the first bit is always 0? Because all the addresses, they are even. Why the addresses, they are even? Because each instruction can take 2 bytes or 4 bytes. So the number of bytes needed per instruction is even. So all the addresses of the instruction will be even. So that's why we can use 20-bit for the address, and we know by default that the first bit is 0. So 20 plus the first bit, here we have 21 bits. So with 20 bit, we can go anywhere because the first bit is always 0. So since we can go anywhere, no need to write relative address. In that case, we can directly write the absolute address. Yani, what does mean the absolute address? So the address that you have here, which is the target address. So if you have, for example, instead of B and Z again, if you have Goto again, so instead of writing the relative address of again, we write the absolute address of again, which is in that case 6. Let's see example to understand. So this is the Goto. So we have 2 parts. We have 4 bytes. So the first part here is opcode. This part here is opcode. The rest will be for the address. Okay. Now, how to find the 21-bit address? We have from K0 till K19. Here we have 20-bit plus the first bit, which is 0. Let's take an example to understand how to do. Okay, let's take the example with the call. Okay, so it is almost the same. Okay, so we can use the Goto by returning to the same line. So if we make the label here, we can use Goto, the same label here, or we can use Goto $. Okay, so I don't prefer using Goto $, because some instructions, they take 2 bytes, some other instructions take 4 bytes, so you can be in trouble by using the Goto $+1, $+2, +3, etc. So it is better to use the labels. Okay. Now we have seen the unconditional jump instruction. We have seen the conditional branch instruction. Now let's see the call instructions and how the call instruction work with the stack memory. So generally, if you want to make a good program, we have to make the main program, and we have to prepare different subroutines. And the main program will be calling these subroutines. So if you make program structured like this, so we have subroutine 1, subroutine 2, subroutine 3, etc. And you have the main program. So the main program is calling the different subroutines. So here we have more structured program. Okay, so the advantages are they have more structured program, and we save memory space. How can we save memory space? By using the subroutine, Shabab. How can we save memory space? By using the subroutine. So if you have a program, and this program is calling, for example, the subroutine 1 10 times. Okay, so in that case, we have to write the subroutine 1 just 1 time. Okay, so the size of the code will be reduced. So we are reducing the size of the code. So that means we are reducing the ROM memory needed to store this code. Okay, but the execution time, it is almost the same. So we can write the code 10 times and execute it line by line, or we can write the code just 1 time and call this subroutine 10 times. So the execution time will be almost the same. Okay, but we have a gain in terms of memory space or ROM space. Okay, so this technique permits us to prepare each subroutine in separate module. So we can test each subroutine separately. And if you have, for example, a group of engineers working on big project, so we can divide the project into different subroutines, and each engineer will take in charge some subroutines. Okay. واضح شباب؟
واضح.
Okay, that's great. So let's see how to use the call and the Rcall. So we have two instructions for making the call. We have the call itself and we have the Rcall. So let's open the data sheet to check the difference between them. So here we have the call instruction. This is the call and this is the relative call. So for the call, how many bytes do we need? How many bytes do we need for the call instruction?
Four bytes.
Bytes. Okay. And for the Rcall, how many bits do we need?
16-bit, 2 bytes.
16 bit. And for the Rcall, we need only 2 bytes. So same thing. So the difference here is that the Rcall is relative call, so it is short jump, whereas the call is long jump. So how many bits do we have to write the address in the call? So I have 20 bits from K0 till K19. So since we have 20 bits, we can write any address. So to do this, we can write directly the absolute address, so no need to write the relative address. Is this clear, Shabab?
Yes.
Okay, let's return back to the slides. So this is the opcode of the call instruction. Okay, so I have 1110, and then we have 11. Let's correct this. Then we have 110 S. So S is for the shadow register. Let's make it for the moment the default value, which is 0. Okay. So here, let's suppose that we have 1100. Okay. And then we have the rest of the bits. Now, when we call a subroutine, so the last instruction of the subroutine should be return. So I can see here that each instruction has the return as last instruction. So where to return? For example, here we have this program. So we have call subroutine 1. So from here we will jump to the subroutine 1. We'll execute the program of the subroutine 1. Then we have return. So we have to return to this line. So how can we know the address of this line? We have seen that to do this, we have to use the which memory? We have to use the stack memory. So before jumping, the peak will save this address, let's call it address 1, to the stack memory. Okay. So now before making this jump, the peak will save the address 1 to the stack memory, and we'll jump to execute the subroutine 1. Then we have return. So where to return? So the CPU will take the return address from the stack memory. Okay, so if you have call, now, okay, so we have here the program counter. So if you are executing this instruction, what is the counter of the program counter? Which is the address of the next instruction. So the program counter here is a register, which is 21-bit register that has the address of the next instruction to be executed. So here, how to save the value of the address 1 to the stack memory? We have just to take it from the program counter to the stack memory. So this is if you have call. So if you have call, we are just taking the value from the program counter and pushing it to the stack memory. Then we will jump to the subroutine, we will execute the program of the subroutine, and finally you have return. So how to return? You have to return to the instruction having the address 1. How can we do this? We have to take this address 1 and we have to copy this address to the program counter. Now, if you copy the address 1 to the program counter, that means the next instruction to be executed is the instruction with the address 1. That means we will jump and we will execute this instruction. So if you have call, we are taking the value from the program counter and pushing it to the stack memory. And if you have return, we are retrieving the value from the stack memory and we are copying it to the program counter. So this is the relation of the call with the program counter register with the stack memory. So the program counter is 21-bit register. Why is it 21-bit register? Because it will hold an address. So to hold an address, we have seen that in the ROM we have 2 mega address. So how to write 2 mega? We have seen that it is 2 multiplied. So the mega is 2 to the power of 20. Shabab, after 10 minutes, you can use the same link to connect again. Okay. Now,
Okay, Doctor.
we have 2 multiplied by 2 to the power of 20 address. So it is 2 to the power of 21 address. So we need 21 bit to select one of these addresses. So the bus connecting the stack memory to the CPU is 21-bit bus. Okay. So same thing, we are taking a value of the program counter, which is 21 bits. So here we have 21 bits also. So the number of bits of the stack memory is also 21 bits. And how many levels do we have in the stack? We have up to 31 levels. So when do we need these levels? So we need these levels if you have multiple or nested call. Now here we have subroutine 1. This is subroutine 1. Let's suppose that here the subroutine 1 is calling the subroutine 2. So before jumping to the subroutine 2, we have to save the address of the next instruction, which is, let's call it address 2. So we have to save, we have to use another layer, another level to save the address 2, etc. So we can have up to 31 nested calls. So the stack memory is 21 by 31 memory. Okay. So this is the call. We have seen the call. Okay, so I explained this. So you can see that the stack memory is 31 by 21 memory, and the data bus connecting the CPU, the stack memory is 21 wire, because the data here is an address, and to write an address we need 21 bits. Okay, so the first address will be at address 0. Okay, and the last address will be, what is the last address? So here we have F, and here we have 1. So we have 5 F, and then we have 1. So each F will be written by using 4 bits. Okay, and this F will be 4 bit, 4 bit, 4 bit, 4 bit. We have 4 times 5, we have 20 bit plus this bit, which is the bit number 21. So the last address will be 21 bits. Okay. So the stack and the pointer. So I explained it. This, so the stack is 21 by 31. There is a register that point to the stack and use it to access it, and it is called the stack pointer register. So this is very, very important. Okay, so here, when we save the first address, we have a pointer here, call it SP, so the stack pointer. So anytime we save an address, anytime we have a call, we have to increment the stack pointer. That means we have, we start from the beginning. We have call subroutine 1. So we have to save the address 1. We save the address 1 and then the stack pointer. So the stack pointer was here pointing to nothing. And if there is a call, the stack pointer will be incremented. So now the value of the stack pointer is 1. That means we are pointing to the address 1. If there is a return, we will return this address. Okay. Now, if we suppose that subroutine 1 is calling subroutine 2, so before this return, we have called subroutine 2. So we have to save the address 2. So if you save the address 2 by using this call, the stack pointer is incremented. So the stack pointer will be here. So its value will be 2. That means we are pointing to the address 2. So if there is a return, we have to return the address 2. So anytime there is a call, the stack pointer is incremented and we are pushing an address to the stack memory. Anytime there is a return, the stack pointer will be decremented and we are retrieving value from the stack memory. So you can see that this memory is last in, first out. So you have last in, first out memory. Yani the last instruction or the last data that get in is the first data that gets out. So we are taking always the data from the top of the stack memory. So the stack pointer is in a special function register at this location, call it stack pointer, and it is 5-bit register. Why 5-bit? Because we have 31 locations. So storing the CPU information, such as the program counter on the stack memory, this is called push. So if we are adding an address to the stack memory, this is called push. And retrieving value from the stack memory, this is called pop. Okay, so we can push an address to the stack memory. This is the stack memory. So we can push an address or we can pop an address from the stack memory. So this is how does it work. So stack memory have 21 bits with from A0 till A20, and the levels from the level 1 till the level 31. Any question about this? Okay, so the stack is last in, first out memory. So the stack pointer point to the last used location. And this is called the top of the stack. When data is pushed onto the stack pointer is incremented. When data is popped from the stack pointer is decremented. So when a call is executed, the content of the program counter is pushed onto the stack, and I explained this. And when there is a return, the content of the top of the stack, and the value that we have in the top of the stack, it is copied to the program counter. Now let's see an example. So here we have an example to toggle the bit of port B by sending continuously the value 55 followed by the value AA. And you have to answer the delay subroutine in between. Okay. Sorry, Shabab. Okay, Shabab, sorry. So here we have just to send the value 55. We have to send the value 0x55, and then we have to send the value 0x AA. So 0x55, then we have the delay. We have to call the delay, then we have to send 0xAA, and then we have to call the delay, and this will be within the loop. Okay, so the program is very simple. So first of all, we have the delay subroutine. So this is the delay subroutine. So we have just one loop doing nothing. Okay. So we have to initialize the counter by FF. Okay, and then we have two no operation, and we have to decrement 5, myreg and branch if not 0. So this is the delay subroutine. And the main program is loading 5.5 to port B, move LW55, move WF port B, then call the delay, move 0xAA, move LW0xAA, move WF port B, and then call the delay. And we have to do this within an infinite loop. Okay. Shabab, let's connect again by using the same link. Okay.
Okay.